Hello, today's lesson is on bonding. More specifically, this video is going to be on ionic bonding. So I'm going to talk a little bit about the intro to chemical bonding and then focus mostly on ionic bonding. And then the remainder of this unit pretty much is dominated by the molecular bonding or covalent bonding. Okay, so chemical bonding. We're looking at atoms being joined together to create compounds, and that's what a chemical bond is. It's basically a force that's going to hold two atoms together. Now, when these atoms are held together, there's three different types that we're going to end up with. We're going to end up with what's called ionic bonding and what's called covalent bonding. Okay, but now covalent bonding actually breaks up into two classes because of the way they share electrons. And what we end up with is electrons being shared or sharing electrons equally, and that's going to give rise to what are called nonpolar covalent bonds. Okay, and then down here we have our polar covalent bonds because what's going to happen is two elements are going to share electrons unequally. And we'll talk about this more in the molecular video on molecular bonds and covalent bonds. But for now we're going to focus on strictly on ionic bonding. So this is where the electron is completely removed from one atom and put into another atom, and we end up with a positive charge and a negative charge. Now this is a full charge, not a partial charge like over here. That's what this little symbol means. It means a partial charge. Over here there is no partial charge because both sides are evenly distributed, and that's if you look at this blue and red. The blue is the negativity and the red is the positivity. If you look over here, we get a positive end over here. It's not as red as over here, and we get this blue side, and we get a gradual change throughout the molecular structure. And as we look at bigger and bigger molecules, we look at how that's arranged throughout the more complex molecule. Okay, so those are your three types. Let's focus on ionic bonds and talk about the basics of that. And it really comes down to the fact that and again, what we're looking at are charges that are already formed. Okay, so we have sodium reacting with chlorine, okay, to create sodium chloride. And what we end up with is sodium chloride already bonded together in this solid substance over here. All right, so we're talking about this side here. We're talking about those charges that are already created, okay, that bond that's holding them together. Since we already have a positive and a negative charge, we're going to treat this just like we do in physics. Okay, when you have a positive charged particle interacting with a negatively charged particle, there's a force of attraction here, and that's what this is. There's an energy associated with that attraction force. And since we're treating these as if they were positive and negatively charged particles, we can go ahead and just use what's called Coulomb's law for that. Okay, and Coulomb's law is this equation. Now, with this equation, you're not going to have to do any calculations. They're not going to ask you to plug it in, but I do want to use this as a centerpiece for our understanding. Okay, so we talk about ionic compounds. We're just going to arrange them positive, negative, repeating over and over and over again. This negative charge attracts all positive charges around it, so it gets completely surrounded with positive and negative charges. So positive is surrounded by negative, negative is surrounded by positive, and it keeps repeating itself throughout the entire crystal structure. We say that this is a lattice structure. Okay, so we call this a lattice structure. Okay, and that lattice structure, that ionic compound structure, is going to have a amount of energy to it, right? It's going to have a specific amount of energy. So the energy that's holding this lattice structure together is referred to as lattice energy, and that's what the E over here is. We're going to call this lattice energy. Okay, and the lattice energy is the energy that's bonding these ions together. Now, if we look at the entire structure, we would obviously be looking at molar amounts, but this equation here is actually going to show us the relationship between two charged particles, and then we would obviously, magnify it depending on how many particles we have. Okay, so if we're looking at this equation, there's two things that we want to look at. Okay, one is Q. And Q is the magnitude of the charge. So that is your charge of the particle. As I said, you're not going to have to plug this stuff in, but it simply is the positive or negative charge. So it's the charge of the ion. We're going to stay with ions because that's what we're talking about in chemistry. So it's your charge of ion. So if I have a plus 1 and a plus 1 and a minus 1 charged particle like I do in sodium and chloride, well, there's a certain amount of energy that I would have it. But if I compare that to magnesium and oxygen, well, now I have a 2 plus, 2 minus, therefore I'm going to get more energy. So our first lesson here is that the higher the charge, right, if Q is larger, right, if the charge is greater, Then our lattice energy. I'm going to use Le for lattice energy. Now, I probably should have said that. This would be lattice energy here. Okay, our lattice energy goes up. Okay, so if we're comparing sodium chloride to magnesium oxide, we can easily say that magnesium oxide is going to have a higher charge, so therefore it's going to attract more and create a stronger or higher lattice energy. Okay, so that's the first part. Okay, we would look at how these two charged particles, the magnitude of their charge. The second one is R, which is the distance between the nuclei, or in this case, distance between ions. Okay, so we're looking at the distance between the ions. That's what R is. So if we think about it in the calculation, if R goes up, if we get a larger and larger distance, our lattice energy is going to go down. Okay, so therefore we would want our particles, if we want to get the maximum amount of lattice energy in an ionic structure, we want a high charge with very small ionic radiuses, right? We want the particles to be very close to each other. Okay, I can show you an example of what I'm talking about here. So let's look at ionic radius here. So again, we're using this equation. All right, we're going to start with, I have over here, I have lithium, I'm sorry, not lithium, but I have sodium. So I have sodium, nope, not an S, what am I doing? I teach chemistry, I should know that's an Na. Okay, so that's sodium fluoride. This is sodium chloride. This here is sodium bromide. And then down here we've got sodium iodide. So what I'm doing is I'm going down that group on the periodic table, the halogens. So when sodium combines with fluoride, okay, we can see that the atoms are pretty close together, right? And I shouldn't say atoms, but I should say ions. The ion radius is pretty close in size. So therefore, when I look at going to chlorine, as I go down the periodic table, the ionic radius increases, right? Because I add an energy level and I get a bigger chloride ion and a bigger bromide ion and a bigger iodide ion. So if I look at the lattice energy, what's happening is that those nuclei that are inside the ions are getting further and further away from each other, and therefore, as I go down this list, R is going to start to decrease as I go down, right? Oh, I should say that, my fault. R is actually going up, right? The lattice energy is going down. So as I go down the periodic table, my radius is going to get larger and larger and larger, and therefore my lattice energy goes down and down and down. So as the ions get bigger, the lattice energy goes down. We can see that same data with lithium and potassium compounds as well. Alright, so simply speaking, for ionic compounds, we're just really going to be looking at this equation. Now, I wouldn't necessarily commit this to memory. And by the way, K is just a proportionality constant that has been discovered by Coulomb. Again, we're not going to calculate this. All you're going to really need to talk about is, think about it. The closer the ions get, the stronger the bond is going to be. So the smaller the ions are, the more energy they're going to release, and that's what R is showing us. Q is the magnitude of the charge. So if I'm comparing elements together, what I'm looking for is I'm looking for the charges. So what happens if my charge goes up, but the radius goes down? And that question kind of comes up a lot if you're comparing. What I would do first is I would take the charges. Charges are going to override radius first. So if you were comparing something like sodium bromide to something like magnesium, well, right away, because magnesium has a +2 charge, that's going to go ahead and outweigh the distance of the particles. So I'm going to say magnesium, because of the +2 +1 charge, sorry, +2 -1 charge, that is going to have a higher lattice energy. Okay. Only use R if you're comparing something like magnesium bromide to magnesium chloride. Then what I would do is I'd say, okay, charges are the same. Okay, so therefore I'm going to have a +2 -1, and therefore I would look at the ionic radius and say that bromine is going to have a bigger ion, and therefore it would be further away, and my higher energy would be in the chloride. Okay, that's pretty much ionic compounds. In the next video I'll talk about covalent bonds, and I guess that's pretty much it. Thanks a lot.